Hepinize merhabalar. Ben Kocaeli Üniversitesi Elektrik Mühendisliği bölümünden Ragıp Öztürk. Bugün sizlerle birlikte tekrardan veri merkezi hakkında bilgiler edineceğiz. Ben İngilizcesini Türkçe'ye çevireceğim. Bugünkü konumuz veri merkezi HVAC soğutma sisteminin CFD'yi videosunun çevirisini yapacağım. Beni dinlediğiniz için şimdiden teşekkür ederim. Fazla uzatmadan kaydıma başlıyorum.
Hey there guys, Paul here from the engineeringmindset.com. In this video, we're going to be looking at data center HVAC with a focus on the cooling systems used. We'll compare how the different strategies work and how to improve the efficiency, especially with the new growing trend of using computational fluid dynamics or CFD software. And we'll also run some simulations to show just how powerful this is. Data centers are rooms of computer servers which provide networking and internet-based services. They range in size from a small single room serving a single organization, and they scale all the way up to enormous internet giants such as Google and Facebook. More and more data centers are opening each year as we use and increasingly rely on the internet and remote services to store, access, and stream our data. With this growing trend, it's important that the buildings run as efficiently as possible. As the data centers are operating 24/7, they can consume vast amounts of electricity, and as this electricity is used to power the servers and process all the data, it generates a lot of heat. This heat needs to be removed, otherwise the electrical components will overheat and fail or even catch fire. The energy consumption for a typical data center will be split with around 50% being used by the IT equipment, 35% on cooling and HVAC, 10% on electrical infrastructure and support, and around 5% on lighting. The electrical demand for data centers really does vary from just a few kilowatts up into the megawatts depending on the size and the location. So we're going to look at a few examples of data centers and their air conditioning systems, as well as the efficiency improvements that can be made. The first part we'll briefly cover is the non-data hall areas. These are the areas where staff are normally located, the security guards, the engineers and technicians, etc. And these cover the areas of the offices, the toilets, the workshop and rest areas. These areas will be served by a separate mechanical ventilation system and will use either an air handling unit or a rooftop unit to distribute conditioned air to suit the thermal comfort needs of the humans. They might also use a separate split unit heat pump or VRF system for temperature control in these areas. I won't go into too much detail in this segment as we've covered these in our previous videos on chillers, AHUs, RTUs. We also have videos on VRF, heat pumps and split AC units. If you want to learn more on these, links are in the video description below. Coming over to the server room, one of the most common methods currently used is to place the server racks onto a raised floor and then use computer room air conditioners or crack units to distribute the conditioned air to the server racks. The crack units have heat exchangers inside which are connected to refrigeration units or chilled water systems to remove the heat from the server racks. Some can also humidify or dehumidify the air. That's very important in order to control the static electricity in the air. They have filters inside to remove dust from the room as well as a fan to circulate and distribute the air. For extra efficiency, the crack unit should use energy-efficient filters, EC or electronically controlled fans, and pressure sensors in the floor void to precisely control the air supply rate. Placing temperature sensors on the intake walls of the server rack is often recommended to control the supply temperature from the crack units, as this matches the actual intake. The conditioned air will be forced by a fan in the crack unit into the void under the floor, and the small holes or grills in the floor tiles will allow the air to leave the void in strategic places. This air will collect the heat and rise up towards the ceiling. The crack units then suck this warm air back into the unit to be reconditioned. In the early days, the server racks were positioned facing different ways, and engineers soon realized this was very inefficient because the fresh cold air was just mixing with the warm discharge air of the servers, and this meant that the servers were receiving different air temperatures, some hot, some cold, and this led to high energy consumption as well as the high failure rate of the servers. To combat this, the servers were positioned so that all the server racks were facing the same way. This was a slight improved strategy, but quite often some of the discharge air was being pulled into the intake of the server rack sitting behind it, which led to mixing and an increased air temperature. The next strategy used, which is still very common today, is the use of hot and cold aisles. This is a great improvement on previous designs because it separates the fresh cold air stream from the hot discharge air. The cold air rises out from the floor grills and is pulled through the servers. All the hot discharged air collects into the hot aisle and rises up towards the ceiling, where it is then pulled back into the crack units. This means the servers should receive only fresh cold air and the crack units receive the hot discharge air. This increases the temperature differential across the crack unit's heat exchanger, and that will improve the efficiency of the machine. This is not perfect, however, because there will still be some mixing of the hot and cold air streams. Cutouts in the floor can result in air leaks. This means that the cold air can leak straight into the hot aisle. Floor grills, which are too close to the crack units, result in air recirculating straight back to the crack unit and will mix with the return airstream. Gaps between the servers can result in air recirculating around inside the server. This can easily be solved though by installing blanking plates. If more cold air is supplied than needed, it will flow over the units and mix with the discharge line. If insufficient cold air is supplied, then warm discharge will be pulled over the top and around the side of the server and into the cold aisle and will mix with the stream. We're going to look at some CFD simulation examples shortly of this occurring. A much improved design, and one that is very popular currently for both new and existing data centers, is to use a physical barrier to separate the two air streams. There are a couple of ways to do this. We can use a barrier around the server rack and then contain either the hot air or the cold air. Cold air containment is a very popular choice for existing data centers. That's because it is easy and cheap to implement, which means the payback is quick. The cold air fills the cold aisle, and then the hot discharge fills the rest of the room, with the crack units pulling this in for reconditioning. However, it does also mean that any equipment located outside the cold zone will only receive hot air. The other containment strategy in use is the hot aisle containment. This is best suited to new builds as it costs more to install. In this strategy, the cold air fills the room and the hot discharge air is pushed into another void within the ceiling. The intake of the crack unit is also ducted into the ceiling to pull this hot air out for reconditioning. The hot aisle containment provides superior performance and also allows a slight buffer for cooling should the power or cooling system fail. We can actually compare the performance of different server room setups quickly and easily using CFD or computational fluid dynamics. These simulations on screen were generated using a revolutionary cloud-based CFD and FEA engineering platform by SimScale, who have kindly sponsored this video. You can access this software free of charge using the links in the video description below, and they are for a number of different account types depending on your level. It's not just limited to data center design, it's also used for HVAC, AEC, electronics design, as well as thermal and structural analysis. Just a quick browse on their website and you can find thousands of designs for everything from race cars, heat exchangers, pumps and valves, which can all be copied and used as templates for your own design. They also offer free webinars, courses and tutorials to help you build and run your own simulations. If, like me, you have some experience with creating CFD simulations, then you'll know that normally this kind of software is very expensive, and you would also need a powerful computer to run it. SimScale, however, can all be done from the internet browser, and as they're cloud-based, their servers do all the work, and we can access our designs from anywhere, which I'm really pleased about as it makes our lives as engineers a lot easier. So if you're an engineer, a product designer, a student or a hobbyist, then I highly recommend you try this out. Get your free account by following the links in the video description below. Okay, so the first design, we've used a standard hot aisle configuration. The arrows indicate the direction of flow and the colors indicate the velocity. You can clearly see there's a huge amount of recirculation occurring between the aisles, and I've highlighted these in the boxes. The second design uses partial hot aisle containment, with the third hot aisle at the ends being uncontained. You can see the first hot aisle has a very good profile and no recirculation is occurring. The second aisle, however, there is some recirculation occurring towards the end of the row, so some steps like blanking plates need to be installed here. The third hot aisle has some major recirculation occurring, and that's because there is no physical wall to separate the hot and cold air streams. If we then run a simulation for thermal analysis of the designs, we can compare the two designs and show the resulting temperature distribution at different levels. The simulation starts at floor level and moves up to the top of the racks. From the comparison, we can clearly observe that at the lower levels, the second design has a much cooler cold aisle as compared to the first design. As we move to the upper levels, the air temperatures start to mix, but the second design still maintains much cooler levels, well below 28 degrees Celsius or 80 degrees Fahrenheit, whereas the first design has temperatures above 29 degrees Celsius or 84 degrees Fahrenheit. The recommended ranges from standards require that the inlet air temperature be within 18 to 27 degrees Celsius or 64 to 80 degrees Fahrenheit. At the very top levels, the temperature for the first design are now in the hotter range of 40 plus degrees Celsius, or
104
104
Fahrenheit
degrees
derece gibi daha
Fahrenheit,
sıcak
while the
arada
second
iken
design, the partial containment one, is
maksimum
only a
sıcaklık
maximum
sadece
of
30
30 degrees
santigrat derece
Celsius or
veya
86 degrees
86 Fahrenheit
Fahrenheit.
derecedir. Bunun
Thus, the
nedeni
second
ikinci ısınan
design
bu durumda
performs much
çok
better
daha
in
iyi
this case, and
performans
further design
sağladığı
improvements
için.
such as full
Soğuk
hot aisle or
koridorun
cold aisle
muhafazlığı gibi
containment
daha
can
çok
be studied using cloud-based CFD
ve
to
veri
improve
merkezinin
data
soğutmasını
center cooling,
iyileştirmek
as
ve
well as optimizing energy consumption of both the
ekipmanların
server
hem soğutma
equipment
ülkelerinin
and cooling
enerji
units.
tüketimini optimize etmek için
Another type
veri
of
merkezi
data center
tasarımının
design,
giderek
which is
de
becoming
daha
increasingly
çok
popular, is
yoğunlaştığı
free and
serbest ve
evaporative
buharlaştırıcı
cooling. It can
soğutmaların
be
bazı adı
retrofitted in
konumlarına
some existing
uygulanabilir.
designs, but it's especially
Özellikle
popular
Facebook, Google
with
gibi
large
büyük,
new
özel
purpose-built
alan
data
inşa edilmiş
centers
veri
like Facebook
merkezlerinde
and Google.
popüler.
Some
Bu
of
yeni
these new
tasarımlardan
designs
bir
do not use
kısmında
any
soğutma amaçlı
refrigeration
herhangi bir
equipment for
soğutma
cooling.
ekipmanı kullanılmamaktadır.
This can only
Bu
be done in
yalnızca
some regions of the world where
ortam
ambient
koşullarına
conditions
uygun
are
olduğu
right, but it allows data
veri
centers to cool their
merkezlerinin
servers without any
herhangi bir
refrigeration
sorgulama
plant.
mekanizmasına
The
ihtiyaç
ambient air
olduğu
is sucked
ortam
into the
havası
building through some louvers, and it's
soğutucu
then heavily
tarafından
filtered and
yoğun,
cooled and
soğutabilir ve
humidified by
nemlendirilir.
evaporative coolers, and then
Ardından
forced
sıcak
into the
koridor
data hall into a
konfigürasyonu
hot aisle
sağlanabilir.
configuration. The
Sıcak
exhaust
koridora
of the hot
egzoz
aisle is
daha
then
sonra
connected to another set of
sıcak havayı
fans,
dışarı
which
çeken,
pulls the hot air out and discharges
atmosferde
this off into
boşaltan
the atmosphere.
bir fan setine
Some
bağlıdır.
other cooling strategies which are
Diğer
slightly less
soğutma
common are the use of
sistemlerinden
ducted systems with
ısı
heat wheels or
tekerlekleri
heat
veya ısı
exchangers
şarjına
fitted.
takılı
These
kanallar
allow thermal
binaya
energy
taze
to be
hava girmeden
transferred from one
bir
stream
akımın
to
diğeri
another
aktarılmasını
without
sağlar.
introducing fresh air into the building. The fresh air
Elektrik
can contain
bileşenlerine
dust,
zarar veren
moisture,
toz,
and
nem ve
salt
tuz
particles,
parçaları
which
içerebilir.
deteriorate the server's electrical components. To
Çatlak
provide
ünitelerin
cooling to the
soğutmasını
crack units,
sağlamak
you'll usually find a
genellikle
chilled water system using a
soğutucu kullanımı
traditional
soğutulmuş
chiller.
su sistemi
Depending on the
kullanılır
location,
ama bağlı
some
olarak
systems
bazı
are able
fanlar
to turn
soğutucuları
off the chillers
kapatabilir.
and use just the evaporative
Ve
cooling
normal
capacity of the
çalışma
cooling
için sadece
towers for
soğutucu
normal
ve
operation, then use
buharlaştırmaları
the chillers as
yapılabilir.
their
Daha
backup
sonra
if the
soğutma
cooling
kuleleri
towers are unable to reach
ayar
the set
noktasına
point.
ulaşmazsa soğutucuları
Some crack
bazı
units
çatlak
contain their
üniteleri
own small individual refrigeration system, which either uses
uzaktan
a
kuru hava
remote dry air cooler or
kullanılan
they
veya
dump their heat
ısıları
into a
kondansatör
condenser
sisteme
water
aktaran
system.
kendi küçük
If a condenser system is used,
kondansatör
then you'll
sistemine
often
bağlıdır.
find a free cooler connected to the system or
Soğutma
sometimes
içine
built into the
yerleştirilmiş
chillers. This
ücretsiz
allows the heat to
bu
be removed
kompresörü
without or
az
with
kullanımıyla
minimal
veya
use of a
daha hiç
compressor, using
kullanılmamış
just the fans to blow
fanları
cooler
kondansatör boyunca
ambient air across the
uzaklaştırılması.
condenser
Bu da